these days, most people, when they hear the words AI, they think about machine learning or statistical methods in general. But of course, there's an older tradition grounded in mathematical logic, where we can actually have strong mathematical guarantees about whatever conclusion some system has drawn. And related to that is this area of formal methods, where we want to do mathematical proofs about the correctness of the software that we rely on. I think that area has some similar reputation today to what neural networks had in maybe 2010, where actually there's quite a lot going on already, but most people think of it as a kind of an also-ran, but also it might be just about to break out in a big way. Last year at this event, I talked about our project building formally verified cryptographic software that is installed in most consumer devices that they think of as computers today in web browsers. And I want to update you on some other stuff that we've been involved in that subject matter recently. So when I started in grad school, it was already standard. When you give a talk about mathematical methods to avoid bugs in systems, you have the scare slide that flashes up some news articles and so forth about some consequential bugs that have gone down recently. Here are a few. It's natural to ask the question, can we come up with principled methods of developing computer systems where actually we're much less likely to be surprised by bugs that have big economic consequences? That's what most of my research is about. And we all know it's pretty hard to build significant software programs that are not full of bugs. We can do our best in totally unprincipled ways and sometimes get more or less reasonable results, but systematic approaches like testing and debugging can make a big difference. Nonetheless, they're always a little, they make us nervous because we can, for instance, forget to include a test that covers some important corner case. And so formal methods is a systematic approach to being sure that you can get guarantees about all possible executions of a system because you do a mathematical proof instead of just poke it over and over again. And nonetheless, with formal methods, where you write a program that understands programs, you have to wonder, is my program understander now buggy? Is the compiler that I use on the code that I prove buggy? If either of those is true, then you voided all the warranties and you don't know what you've learned. So there's an alternative approach of end-to-end mechanized proofs that most of my research is about that tries to reduce trust requirements as much as possible. So what you do here is you have the team of engineers building an artifact, not just creating the code in the normal sense, but also they write down a mathematical proof about why that artifact meets its requirements. And then you can feed that proof as a consumer of the system to a proof-checking algorithm. I'm not talking about proofs in the normal way mathematicians work with them, where people pore over journal papers and look for bugs. That's a pretty imperfect process. We can actually use an algorithm to check totally rigorous ASCII format of mathematical proofs to show that significant components of systems do what they're supposed to do. So here's an example of a prototype we built a few years ago. We call it the Verified Internet of Things light bulb. At the top there, you see a network card, and at the bottom right, a power strip with a light bulb plugged in. And this is a system whose job is to accept light bulb turn on off requests from the network, execute them, and do nothing else. We have an FPGA, a reconfigurable hardware platform down there at the lower left, connected to these two pieces, and its mission is, right packet comes in, light bulb turns on, and you can imagine there's the reverse of that process too. And what we did is we carried out one totally rigorous mathematical proof, checkable by an algorithm, that everything digital loaded on that reconfigurable hardware platform down there functions together to do exactly what it's supposed to do here. Turn the light bulb on and off when the right network messages appear. And it's a pretty big engineering undertaking to construct a proof like that covers all the details. And so we built around this open hardware instruction set called RISC-V. We built and proved a processor that implements that instruction set. On top of that, we have a C-like software programming language called Bedrock, which has its own formally proved compiler. And then there's the application software and the device drivers written in that language, which are themselves proved. And then importantly, all these separate formal results are connected to each other. So there are a bunch of interesting technical questions that come up in that kind of effort. I just want to focus the most on the last one in this bullet list, formally capturing how different layers in that picture make assumptions about their neighbors so that you avoid bugs that arise only in the integration process where each piece individually might have seemed correct. There are a bunch of sort of logic engineering techniques that go into doing that right. And when you succeed in it, what you get is this lovely result that all the pieces in the middle of this picture don't need to be trusted anymore. You're guaranteed that if you manage to carry out this proof, you've caught any consequential bugs in the middle parts. Like, you don't need to trust your processor or your machine code format or your software programming language or compiler anymore, because if you formalize the top and the bottom parts correctly and manage to prove that all the stuff in the middle gets you from the bottom to the top, then there can't be any bugs left that you missed that would lead to invalidating your overall argument. We have also carried out another different kind of case study more recently that pushes it to more complex software, in particular dealing with cryptography here. So we built out a formally verified cryptographic library that includes two of the most important standard cryptographic primitives for the internet. We built an extended network protocol implementation that controls this cute little Lego garage. And as Lego garages tend to have, there's of course a microcontroller on the roof. And its purpose is to accept network messages that ask to open and close the garage door, but it uses a cryptographic protocol to make sure that only the owner of the garage is able to do that because they know a secret key. So we built all the software that goes into that functionality, including some improved device drivers. We used some of the same compilers and other tools from the previous example, and we also built new compilers that process higher level languages to reduce some of the engineering effort that goes into the project. And then all of those pieces get plugged together into one proof that says one native code image you can load onto this simple embedded system exactly implements this protocol and nothing else. And the "and nothing else" part is also important. One last message I want to leave you with. One challenge that I've brushed past so far in this presentation: when you want to prove that a system is correct, you need to formalize what correct means, and we call that a specification. And you might worry that new bugs will be introduced in the specification writing process. And if you prove the wrong theorem, then you may be worse off than before because you have a false sense of security. But there's a really cool benefit of proving almost any detailed behavioral theorem about a real system, which is that doing so rules out some of the most common and consequential sorts of security problems. Let's take the example of a code injection vulnerability where an attacker can send a packet that overflows something and overwrites the code of your program and makes it do something totally different. If you proved your program turns a light bulb off and on and nothing else, then it can't possibly be vulnerable to a code injection vulnerability. If it were, someone would make it do something else, like they'd make it join a botnet. And so if you manage to prove almost any pretty detailed theorem, it could be a little off. Your system might not do quite what you wanted, but it's definitely going to be defended against the most common and important kinds of security problems. And for reasons like this, I am hopeful that this kind of methodology and tooling will become increasingly used to build systems alongside their formal mathematical proofs of correct behavior, and everyone who relies on those systems, if they're open source, will be able to recheck those proofs and not have to trust anything about how the development was carried out. Thank you.